Hello, everybody. In this video, we're going to go over some questions from addition reactions. Okay, so let's start with this question over here. Let me see if I can center it. So here's his reaction, and then you are asked to find which species act as electrophiles in this mechanism. Okay, so what I'm going to do is I'm going to take a picture and try to work on that. So again, electrophiles are what is accepting the nucleophilic attack. Okay, so in this case, we have this double bond, which is going to act as the nucleophilic center. Okay, and then because if you have a double bond, if you have an alkene, the only thing that it could do is act as a nucleophile because it only has an electron-rich region. And then what is happening is this Hi molecule is going to be our electrophile because it is accepting this nucleophilic attack here, right? And then the partially positive charge of hydrogen is going to be grabbed by these electrons of the alkene. That's the idea. Okay, so our first electrophile is Hi. And then in the second step, we can see that we have the nucleophile, which is I minus, okay, and then that is going to that is attacking the carbocation over here, this carbon over here. Therefore, our second electrophile must be this. Electrophile means they love electrons. We have a positive charge. Okay, you love the negative charge, which you find in the electrons. That's the idea here. Okay, so the correct answer for this should be B and C. Okay, let's see, B and C should be our electrophiles. Let's see if we can enter those. B, oh no, it can show the correct answer, so it should be B and C. Okay, so next question, we have the same mechanism. Okay, addition of Hi to an alkene. Okay, so this mechanism is going to be always the same, and then as a matter of fact, actually, is going to the energy diagram or the reaction path diagram will be the same as well. Okay, so the question is which energy diagram corresponds to this mechanism, and let's take a picture again. Okay, so again, in this case, what we have is two steps. Okay, so in the first step, you can see that we are breaking the carbon-carbon bond, one of the carbon-carbon bonds in this double bond, and also we are breaking the Hi bond. And then in the first step, the only bond that is going to be formed is the carbon-hydrogen bond. Okay, between this carbon and then hydrogen. So we have a new carbon-hydrogen bond formed here. Because we are breaking two bonds and then forming only one bond, this first step has to be an endothermic step because we need to spend more energy to break the bonds than the energy released when this only bond is formed. So as a result of that, we can eliminate option C because the first step has to be an endothermic step. And then in the second step, we see that we have a nucleophilic attack. Only thing that is happening in the second step is a bond formation of a Ci bond. Okay, so that step has to be an exothermic step because when the bonds are formed, energy has to be released. Okay, so therefore option A is out. So between B and D, what we need to decide is the overall reaction, whether it's going to be exothermic or endothermic. Now we see that we are breaking overall, let me use a different color. We are breaking overall CC and Hi bonds, and then we are forming CH bond and Ci bond, okay, which are AB bonds. So because we are forming two AB bonds and breaking only one AB and one AB bond, and then because we are breaking one AA and one AB bond, overall we are forming stronger bonds. If the stronger bonds are made, okay, on the product side, of course, you're going to have a lower potential energy on the product side. Therefore, overall, you're going from a higher potential energy to a lower potential energy, releasing energy. Therefore, it's going to be an exothermic reaction. The exothermic reaction shown here is not B, it should be option D. Let's see if top hat agrees with us. So the correct answer for this question is option D. All right, so next question, the rate law for this mechanism. It's the same mechanism. Again, you have only two steps. We already know the energy diagram for this is gonna look something like this. Okay, first step is endothermic because you are breaking two bonds and forming only one bond, and then the last step is exothermic, and it's gonna look something like that. Now we can see that we have a large energy barrier or activation energy for the first step, then for the second step. Therefore, the rate determining step is the first step, or the slower step is the first step. And then in the slower step, the reactants are this guy, the alkene, and then HI. So we have two of them. So therefore, the correct answer must be option C over here. Okay, the rate law for the slower step must be the rate law for the entire overall reaction, and that's why the rate law must be this. Let's see if top hat agrees with us. Great. And then next question, which of the following represents the first step in the addition of water to alkenes under acidic conditions? Okay, so alkene additions, there are only two types. First, addition of, let me take a picture actually. First, the addition of something like HCl, HBr, or HI. That it's going to be two steps like we have seen before. And then the other way is addition of H2O. It's always acid catalyzed. Therefore, we're going to be using H3O plus in the first step. And then altogether, you're going to have three steps. Just remind us about that. Okay, I think many of us can benefit from that. So let's say that this is our alkene. Okay, in the first step, what is going to happen is we have H3O plus. Okay, and then the carbon-carbon double bond breaks, and then you're going to form a bond between the carbon and hydrogen, and HO bond is going to break as well. And then as you're going to get this carbocation, right? Because the carbon double bond breaks towards the terminal carbon. As a result of that, you're going to have electron deficient carbon in the center as the most stable carbocation. And then in the second step, you're going to have an H2O molecule. Okay, a nucleophilic attack of an H2O molecule, giving us this cation. And then in the third step, we have a water molecule acting as a base, grabbing this proton, and then that's going to break this OH bond to its oxygen, forming OH, our alcohol. So that's going to be the case for the water addition onto an alkene. Okay. Now again, the first step is reaction of the alkene with the hydronium ion is H3O plus. So that looks like, now doesn't look like this. Okay, it is not this step. That's going to be our last step. And then it is not this because it should be acid catalyzed under acidic conditions. What we have is H3O plus, because reaction of alkene with water is very, very slow. That's why we have to catalyze that by adding H3O plus. Now for the correct answer is option B. Okay, so with that, let's see what we have here. So the correct answer is option B. Okay, let's try this question. Which of the following processes are likely exothermic? Okay, so now if you have a bond formation, that's going to be an exothermic process. So here we have this is a bond forming arrow. Therefore, this should be an exothermic process. And then in B, what we have is we are breaking carbon-carbon and HO bond, and then forming only CH. This is formed, and this is broken. Because we are breaking two bonds, it's going to be an two bonds and forming only one bond, breaking two and forming one. Therefore, this is going to be an endothermic step because you need to provide more energy to break the bonds and the energy released. And in the third step, this is an acid-base step. Water is acting as a base to grab a proton. And then here, I would say that we are forming, this is a bond forming arrow and this is a bond breaking arrow. But the thing is, we are forming and breaking an OH bond. Both of them are the same. Therefore, I would say this is thermoneutral. Okay, delta H is going to be neutral here. And then in this step, again, we are breaking carbon-carbon bond and HO bond, and then forming only carbon-hydrogen bonds. Because we are breaking two bonds and then forming only one bond, this is going to be endo as well. Therefore, the only multiple answers. Anyway, so I think the only exothermic step here would be option A. Anyway, let's see what top hat has as the correct answer for this. Okay, so it's going to be just A, which is correct. Okay. Anyway, so let's move on to this question over here. Right, which of the following represents the rate limiting step in the addition of water to an alkene under acidic conditions? The rate determining step or rate limiting step is always the first step when it comes to alkene addition reactions, because that will be forming only one bond and then breaking two bonds, right? So let's see again. Now, option A looks correct. Option B is not correct because the arrow should start always from the nucleophile. This is starting from something else, therefore that is out. And then again, option C is incorrect, right? Because you always start the arrow from the alkene, which is our nucleophile. And then option D is starting the arrow from the nucleophile, which is good. But the thing is, the OH bond is breaking towards hydrogen, right? So that cannot happen. The OH bond should break towards the oxygen, so that a proton transfer can take place here. So this is out as well. Okay. And then for an example, electronegativity of oxygen is high. Therefore, when the bond breaks, it should break towards oxygen. And also for our alkene to attack hydrogen, it should have a partial positive charge. Okay. Because if it has if the bond breaks towards hydrogen, it's going to have more electrons, and that is that's not going to interact with the electron-rich alkene. It's going to repel it. Therefore, the bond has to break the other way. Okay, that's why option D is out. Correct answer is option A. Okay, so moving on. Select the major product of the addition of water to this alkene. Again, so when the idea is when this double bond breaks, it can break towards this side or towards this side. Okay, that's the idea. Okay, so then as a result of that, we can have two situations for this double bond. Okay, let me draw at least part of this double bond. So if this is the case, you can have the cation here. Okay, that is if the double bond breaks this way. Okay, or you can have the cation at the terminal carbon. Okay, that is actually, let me use a different color for that. Okay, so let's select green. Okay, if you Okay, you can get the cation on the terminal carbon. Okay, for that to happen, this double bond should break towards left. Okay, so the idea is, if you think about these two carbons, okay, so let's consider this as our R group. Okay, so this is R and R, the rest of the molecule, which we don't care. Now the idea is we have two types of cations here. So this is a secondary carbocation and this is a primary carbocation. So in the primary carbocation, you only have one R group. In the secondary carbocation, you have two R groups, because technically this part is considered as R in this case. This whole thing is considered as one R. Okay, R groups are hydrocarbon groups which are electron donating, that stabilizes the cations. Okay, because you have two stabilizing neighbors, so electron donating neighbors in secondary carbocation, that's going to be more stable. As a result of that, that's going to be formed more. Okay, again, just to remind us, if you think about the formation of the most stable carbocation, it's going to look something like this, the first step. And when it comes to the that's the secondary. Okay, and then when it comes to the primary carbocation, the other option, you're going to have a higher activation energy because it's going to be less stable. So it's primary. Now, because you have a lower activation energy for the formation of the secondary carbocation, or the most stable carbocation in this case, it's going to be formed more, and that's going to be it's going to produce more of the product. Therefore, it's going to be the major product. Therefore, the major product would be this. Okay, so anyway, so that looks like option A over here. So option B is not valid because the double bond or double bond has to go when the addition takes place. And then option C is the minor product, which is coming from the less stable carbocation. And then option D is invalid because, again, the double bond has to go when the addition takes place. Okay, so the correct answer is option A. Okay, so with that, let's move on to the next question. And select the major product for the addition of water to this alkene. Again, if you mark the more the possibilities, all right, so we can have the positive charge here, here, or here, or here. Just the possibilities. Okay, more. So if you consider this positive charge at this place, you're going to have two R groups. Therefore, this is going to be a secondary carbocation, and this should be primary because there's only one R group. And then again, this is secondary, and then this is tertiary. Tertiary because you have three R groups around it if you have a carbocation formed here. Now, tertiary carbocations are the most stable. Therefore, you should have this product for sure. Okay, when this double bond is gone, and then when it comes to the second double bond, the other double bond, secondary carbocation is more stable than the primary. Therefore, you should have an OH here when the addition of H2O addition occurs. So this should be our major product, and then that doesn't look like A because you have this which is wrong, and then it doesn't look like this because this is not the major product of this of the yellow double bond we talked about here, and then it doesn't look like C because this is wrong because this is not the most. This is not coming from the most stable carbocation which was formed here, and then therefore it has to be option D, and yeah, option D looks like what we drew over here. So the correct answer is option D. So moving on, the correct answer must be option D. Okay. All right, let's do this. Which of the following alkenes could be used to produce this alcohol by the addition of water under acidic conditions? Okay, so only requirement is, it doesn't talk about whether it is major or minor. Only requirement is to get a positive charge here. That means a double bond should involve this carbon. That's the main requirement. Okay, now A is good because we have a double bond involving that carbon. Okay, and then B is also good because you can have this this double bond involves this carbon, because if we turn this around, it's gonna look like anyway, look like the OH. I mean our product. Okay, because if we have this OH bond to here when the double bond is gone, and then C would not work. Okay, because you're gonna get not just one. When these two double bonds are gone, your major product would be something like that, which doesn't look like this guy over here. And then D is fine because we have a double bond involved with this carbon, and then when this double bond is gone, you're gonna get an OH here. So A, B, and D should be your answers. Let's see if that works. A, B, and D, right? So the correct answer, A, B, and D. There you go. All right, so here's another one. Okay, let's deal with this. Which of the following alkenes could be used as reactant to synthesize this alcohol? Okay, alcohol by water addition under acidic conditions. It doesn't mention whether it is major product here. It says just, you know, which of these alkenes can produce it. Okay, so technically the idea is to have a double bond involved in these carbons. So you have this here and here, which is good. A is good, and here, that is good. And then here and here, C is good. Here and here, D is good. Technically everything is good. Okay, and if this said only the major reactant synthesize this alcohol, let's say, as the major product, I think this is what the question was intending to ask, as the major product, then things are going to be different. Okay, so the major product, this first one is fine, right? So it's going to be the major product anyway, because it's going to be the most substituted carbon bearing the positive charge. And then so B would not work because the major product of this double bond would be over here, not there. So that wouldn't work as the major product. And C looks fine. C should work. And then D should not work again because the major product of this double bond should be over here, because it's a tertiary carbon which is more stable than the secondary carbon. Okay, so if that is the case, A and C are the correct answers. Anyway, let's see. So I think this was looking for the major product because this came up in service. So yeah, if this was talking about the major products, A and C are the correct answers. But if they're looking for all the possibilities, all of them are possible to get the OH as shown in the molecule and in the product molecule. Anyway, yeah, that's it. So I think we covered some alkene addition reactions here. In the next video, we will explore some more. All right, bye everybody.